All right, let's do section 10.3, page 504, exercise 23, which reads, the approximation e to the x, which goes as 1 plus x squared over 2, is used when x is small. Estimate the error when the absolute value of x is less than 0.1. Now, the first thing we have to realize is that 1 plus x squared over 2 is the second order Taylor polynomial for f of x equal to e to the x, centered at x equals 0. This is important because it means that we can use the remainder estimation theorem, which looks like this. And so Rn of x, the absolute value of that, is the error that we're looking for, that we're trying to calculate. And that's going to be less than or equal to m times r to the n plus 1 times the absolute value of x minus a to the n plus 1 all over n plus 1 factorial. Now this is based on theorem 3, which tells us that Rn of x is equal to the n plus 1 order derivative of f evaluated at c divided by n plus 1 factorial, and that's going to be times x minus a to the n plus 1. Now, if we compare these two expressions, we can see that the n plus 1 order derivative of f evaluated at c is going to be related to m times r to the n plus 1. And so let's see if we can use this information to figure out what m and r are going to be, because those are really the difficult parts of these equations. Well, let's start out by remembering that f of x is going to be equal to e to the x, and that in my equation over here, I'm interested in the n plus 1 order derivative of f of x. Now, one of the great things about e to the x is that it is its own derivative. And no matter how many times I take the derivative, I'm still just going to get e to the x. Now, the r value up there is a factor that we would pick up every time we took the derivative. So for instance, if f of x was equal to e to the 3x, every time I took the derivative, I would pick up a factor of 3. And that's why r is raised to the n plus 1. If I took the n plus 1 order derivative, I would have taken the derivative n plus 1 times, and every time I take the derivative, I would pick up a factor of 3. Now we just have e to the x, so our r value is going to be equal to 1. Now, in earlier conversations in this unit, we've talked about m being some upper bound to the function. Well, we have an upper bound for our x value. X is going to be less than 0.1. So if x is going to be less than 0.1, then the maximum value that our function can have, and remember f of x is equal to e to the x, the maximum value that's going to have is going to be e to the 0.1. So let's rewrite our equation here. We're going to have n is equal to 2 because we have the second order Taylor polynomial, and we're going to have a is equal to 0 because our series is centered at 0. So the error that we're looking for is going to be the absolute value of r2 of x, and that's going to be less than or equal to m times r cubed, because remember, n is equal to 2, r is raised to the n plus 1 power, and 2 plus 1 is going to be equal to 3, times x cubed all over 3 factorial. And now we can just substitute in the values that we've been talking about. So m is going to be e to the 0.1, r is going to be 1, x, well, we're looking for an upper bound to the error, and the greatest value that x can have is going to be 0.1. So if we're going to be using x in the equation to find our upper bound, we want to use the maximum value for x. So we're going to let that be 0.1 cubed all over 3 factorial. And when you plug that into your calculator, we get approximately 1.842 times 10 to the negative 4, and that's going to be the error that we were solving for.